If X is multivariate normal, then it's an invertible linear transformation of an IID standard normal vector. It follows then that if you take a linear transformation of X, then that is also multivariate normal. That is because your new linear transformation is a linear transformation of a linear transformation of Z. And that's another different linear transformation of Z, which by definition is multivariate normal. So the great news here is that if you start out with x1, x2, xn multivariate normal, and I ask you, what is the joint distribution of, let's see, how about x1 and x1 plus x2? Now you can see that that's a linear transformation of your original sequence x. And so without doing any further work, you write down it's multivariate normal. And our job that remains is simply to find the mean vector and the covariance matrix. Well, what's the mean vector? Clearly, properties of means, it's mu x1. In fact, let me call it ex1 because that's what we were calling it. This did not require any properties of multivariate normal, it's just properties of means. And so also, the covariance matrix is going to be, it's going to have the variance of x1, then it's going to have the covariance of x1 and x1 plus x2. And then it's going to have the same thing again. And then it's going to have the variance of x1 plus x2. So where are we going to find all this? We're going to find it in the covariance matrix of X. Where are we going to find variance of x1? It's the first diagonal element. Where are we going to find the covariance of x1 with this sum? Well, we are going to first sort this out by bilinearity. Both of those we can find. This one we already found, variance of x1 we already found. This one is the second element in the top row of sigma. And how do we find variance of x1 plus x2? It's the variance of x1, which we found, plus the variance of x2, which is the next diagonal element, plus twice the covariance of x1 and x2, which also we can find in the first row or in the first column of the covariance matrix of X. So look where you used multivariate normal. Up at the top, you said, if my original X is multivariate normal, and you ask me to find the joint distribution of this vector here, x1 and x1 plus x2, then I just know that that is multivariate normal because it is a linear transformation of my original vector. To identify the parameters of that multivariate normal, which is the mean vector and the covariance matrix, I just need to apply properties of means and variances. This no longer has to do with the fact that I have a multivariate normal. So multivariate normal behaves beautifully with linear combinations, and fortunately for us, many extremely useful random variables happen to be linear combinations of multivariate normals.